Welcome to MEI Modelling with Algorithms. We're on the topic of Graphs and Networks 1, Modelling, and we're on video 1.1, Introduction to Graph Theory. Now, in decision maths, the word graph has a slightly different meaning from its meaning in pure maths. So in decision maths, it is just a diagram made up of dots, which are called either nodes or vertices, and lines, which are called either arcs or edges. And even if the graph is representing something physical or geographic, the graph does not have to be accurate or to scale in any sense. And the graphs that we see are able to model all sorts of different situations and problems. Some of them are very physical ways. There's a very clear link between the graph as a pictorial representation of the actual thing that it's modeling, but it can also be things that are much more abstract, like relationships between people, things like that. Here we have a very famous example of a graph. In this case, the London Underground. You could represent the stations as nodes, and the connections between those stations are the tracks, so they would be the arcs. So this video to a large extent is about getting used to the terminology. So we've mentioned the word graph, we've mentioned that the dots that we draw are called nodes. They're sometimes also called vertices. It may be worth just making a note here of that nodes and vertices mean the same thing in this topic. And then the lines that we see connecting them are called arcs, or they're sometimes called edges. Now, the degree, otherwise known as the order of a vertex, is the number of edges that connect to that vertex. And if we describe a graph as being connected, a connected graph, we can see an example here, then what that means is that it's possible to get from any node to any other node, possibly via other nodes. However, a graph like this one, which is actually just one graph, even though it might look like two, is not connected because it's not possible to get from every single node to every other node. Now, this is the first question we're going to consider. I will tell you now, this is a trick question, but it might still be worth you pausing your video and seeing if you can figure out why that question is actually quite unreasonable. Okay, well, maybe you've tried doing this and you've found it's not possible. It may be tricky to see exactly why, but let's think about this. Let's just draw a few nodes. We don't even need to draw 6. I'm just going to get this basic idea across to you. So suppose those are our nodes. Haven't drawn any arcs yet. As soon as I draw an arc, though, let's look at what happens. So say I draw an arc connecting those two nodes. That means that now this node has got an order of 1, and this node has also got an order of 1. But the total order of the graph, if I add up the orders of all the nodes, the total order is now 2. Okay, what happens if I add another arc? So now this node here's got an order of 1, this node here now has an order 2, and the total is now 4. And if you think about it, that total order is always going to be an even number, because for every arc I add, I'm adding 2 to the total, because each arc's got 2 ends. Now if I look at the numbers here, these orders 1, 1, 2, 3, 4 and 4, if I add those up, I get an odd number, and that's simply not possible. So all you would ever have to say in a question like that, you might be asked, for example, to explain why it's not possible. All you need to say is that the total order is odd, therefore it is not possible. Here's another question for you to consider now. Again, you might want to pause the video in a moment in order to do this. You could do this by just trying to draw a graph that looks like that, or you might want to think whether there's a way of just working out the answer without actually drawing a graph. That's up to you. Pause the video now and see if you can do that. So the easiest way to answer this question actually is to do similar to what we thought about in that first question, which is to take these orders and add them up. So 1, 1, 2, 2, 2, 4, that makes a total of 12. So the total order is 12, and if you remember from what we saw earlier, each arc that we have in any graph joins together 2 nodes. and adds 2 to the total order, that means that the number of arcs must actually be half of that total order. So in this case the number of arcs is 6. And now one more question to consider: can you draw a graph with 6 nodes of orders 1, 1, 2, 2, 2 and 4, if you haven't already? There are 2 at least possible ways of doing this, and actually in a moment I will show you both of these. So if you really want a challenge, try and do one example where the graph is connected and another example where the graph is not connected. Pause the video now and try that. So firstly I'll show you an example of a connected graph that has those orders. There it is. And in doing that, often it is just a case of playing around with the nodes and the arcs. Yours might not look exactly like that. Where you place the nodes in space is not actually that important. That goes back to what we said earlier. And then an example of a graph with those orders that's not connected. There it is. And what you'll notice there is that we've had to use this thing here, which is called a loop. We're going to talk a bit more about those later. Sometimes they're allowed, sometimes they're not, so we've got to assume here that it is allowed. Notice something very important here, which is that the order of that node is 4. You could argue that it should only be 3, because if you only count that loop as one thing, but it's about the ends of the arcs. They're the things that we're counting when we're talking about order. So this arc, because it forms a loop, is actually adding 2 to the total there. So just to quickly say a little bit more about that, in this graph here we see we've got loops. We've also got some which are doubly connected. You can have actually as many connections between the same pair of nodes as you like, so you could have 3, 4, 5, unless the graph is a simple graph, in which case it doesn't have those things. It doesn't have loops, and it doesn't have multiple connections. So it's important to understand, if you're being asked a question that refers to a graph being simple, that that's what that means. Another word you need to know the meaning of is the word complete. It's important not to confuse the word complete with the word connected. A complete graph is one in which every node has got a direct connection to every other node. What you can see in the diagram is the complete graph with 5 vertices there, and the shorthand k subscript n will refer to the complete graph with n vertices. So the graph we can see here is k5. So a question for you to think about now, if you'd like to pause the video in a moment, is if you were to draw the graph k4, and do draw it if it helps, how many arcs will there be? Well, here you can see k4, and if we count these arcs carefully, we find that there are 6 of them. What I want you to think about in a moment then is, what about if we generalize this now to the graph kn? So if you have n nodes in a complete graph, how many arcs will there be? To help you think about that though, think about k4 and just have a look at what's going on here. If we look at each of the nodes, each node has actually got 3 arcs coming off it, hasn't it? Each node's got an order of 3, and that is 1 less than this 4, isn't it? Right? If I was to work out 3 lots of 4, that would actually give me an answer of 12. But of course these arcs are shared, aren't they? Each arc is shared between 2 nodes, so actually we'd have to divide that number by 2 to get the answer of 6. So if you apply that reasoning now to kn, maybe you can work out a formula for the number of arcs in kn. Pause the video and have a go at that if you'd like. Okay, so for kn then, the equivalent of our 3 is going to be n minus 1. and then we need to multiply that n minus 1 by the actual number of arcs in that one, by the actual number of nodes. In this one it was k4, in this one it's going to be n. And then because each arc is shared, we then have to divide that by 2. Okay? And now a couple of other special types of graph that you need to know about. Firstly, a directed graph, or a digraph. This is one where some or all of the arcs have got a direction, and what that means is that they're only going one way, a bit like one-way streets, for example, in a road network. And sometimes that makes sense depending on the context. And then the other type of graph that you need to know about, as well as the others that we've met, is a bipartite graph. And that's one where the graph can clearly be divided into two different groups of nodes, where within each group there are no connections. So here, for example, we can identify these three nodes as being in one group because none of them connect to each other, and then these four nodes are in another group. What you can do if we keep going, there are clearly more arcs that we could add here that would increase the number of arcs, but it would remain a bipartite graph. If we got the maximum number of arcs we possibly could, then that would be the complete bipartite graph, and that uses notation similar to complete graphs themselves, just we need two numbers now for the number of nodes in each group. Now, one important idea in graph theory is that two graphs that are drawn on paper may look different at first, but are actually the same graph. And that's because the physical position of the nodes where we choose to place them on the paper actually is not part of the information that's actually contained in the graph itself. So you could be asked, the way it might be phrased is, which of these three graphs at the top here are isomorphic? So within these three, there's actually a pair of those graphs, which if you look at them in the right way, you realize are actually the same graph. If you want to pause your video for a moment and have a look at those and see if you can decide which pair are actually the same as each other. So hopefully what you can see, now that you've had a bit of time to look at these, is that this graph and this graph, if we're just concerned with what nodes are there and which nodes are connected to which others, they are actually the same thing. Because you see we have this one node on its own there, which is equivalent to that one there, and then that's attached to a triangle, if you like, of nodes, like that, and then that in turn forms this other triangle of nodes here and here. So actually they are considered the same graph, even though at first they look different, and that idea is called isomorphism. And that actually leads nicely to another way of representing graphs. So because all that's really important is which nodes are connected to which others, there's another way of storing the information and recording the information in the graph, and that is to use what's called an incidence matrix. Now what we're going to need to do is label the nodes, so let's do that. So now we've labeled the nodes, in this matrix we're going to record which nodes are connected to which others. Now you'll notice that at least one of these arcs is directed, and so something we need to think about is when we're going from one node to another, we need to make sure we understand which of the two sets of nodes in this table are the ones that we're going from and the ones that we're going to. Now it's entirely arbitrary which way around we do it, but it is important that we make a decision. So if I label this side as from and this one as to, then for example this directed arc here is going from E to C, so I'm looking at from E to C, so I'm looking at this element here, and because there is one arc that takes us from E to C, I'm going to record the number 1 in there. And of course, again, because it's a directed arc, there are no arcs going from C 2e. So over here I'll record a 0. Now for arcs which aren't directed, like for example BC here, well, what you can think of actually, the way you can think about this is when you've got an undirected arc, you could actually think of that as two directed arcs, one going one way and one going the other. Okay, and actually that can help us a lot of ways to when we're analysing a graph in this way. So we've got an arc that goes from B to C, so we've got that one here from B to C, and we've got one going from C to B. So an undirected arc is actually going to create two number ones in our table. Right, now if we look over here, we've got A and B connected by 2. We've got a double arc here, so there are two arcs going from A to B and two arcs going from B to A. So I need to put a 2 in here and another 2 in here. And the one that is potentially confusing here is this one. It's very easy to suppose that this is just going to be a number 1 in this place here, but actually, going back to what I was saying before, an undirected arc can really be thought of as two directed arcs, one in each direction. So this is actually a number 2 that we want to place in that space there. The other nodes don't have loops associated with them, so fairly obviously for A to A, for example, we'll just have a 0. Now, if you want to pause the video and try completing this yourself, just to get a bit of practice, that would be a good idea. Again, if you want to take a screenshot and print it to do that, you can, or just do it on paper. And in a moment I'll reveal the answer. And there it is. Okay, so now we're going to talk a little bit about some more terminology that we use when we're thinking about moving around a graph. So the first word that you need to understand the meaning of is a trail. And that's defined as a sequence of joined up edges such that no edge is repeated. So let's have a look at an example of a trail. Here it is, A, E, B, C, E, D. We just imagine following that then. So A to E to B to C to E again and then to D. We never used the same edge more than once, but we did use at least one of the nodes more than once, which is that node E. So that distinguishes a trail from another thing that you need to know, which is a path. Now a path is very similar to a trail, except that we can't use the same vertex more than once. So that thing there is not a path. This is an example of a path. A, B, E, C, D. If we follow that, we see that we're starting A, going to B, to E, to C, to D. We're following that path. We're never repeating the same node again. You are allowed, however, if you want to, for the first and last nodes to be the same. However, if that happens, then it's actually got a special name, which is a cycle. So a cycle is a closed path. Having defined what a cycle is, it's now easy to define what we mean by a tree, which is another type of graph, but it's a graph which is connected but has no cycles. Now, sometimes these graphs do actually look like real trees, which is obviously where the name comes from, but they don't have to. So for example, this in graph theory is also a type of tree. A spanning tree then is something that we can create from a graph which is not a tree to begin with, where we have to keep all of the nodes, but we can remove some of the arcs until we're left with a tree. And that is actually very useful in a lot of applications to be able to do that. So finally then, just 3 more questions for you to have a think about, and we'll have a talk about these. So the first question is this: how many arcs are there in a tree with 10 nodes? If you'd like to pause the video for a moment now and have a go at that. Now I think trick here is just to keep things simple. We know that a tree can just be a single sort of line of nodes joined together, so why don't we think about what would happen in that case? So imagine if we have 10 nodes all joined together like that, then hopefully it's clear looking at that now that there would only be 9 arcs. You might want to play around with diagrams in your own time and convince yourself that no matter what shape of tree we create, as long as it's a tree with 10 nodes, there'll always be 9 arcs. And then these are the final 2 questions. They both concern a connected graph with 8 vertices. But in the first question we're looking for the minimum number of arcs, and in the second question we're looking for the maximum number, bearing in mind that it's connected and simple. Pause the video now and have a go at those. So for the first one, well, we've just been talking about trees. Trees are sometimes referred to as minimum connectors. So a tree will always give you the minimum number of arcs for a connected graph. So if you've got 8 vertices here, then the tree will have to have 7 arcs. And then for this question, the maximum, well, it's simple, so we can't have multiple connections, otherwise there would be no limit to the number. That means that we must have the complete graph K8, and then if we remember what the formula was that we wrote down earlier, it was n times n minus 1 over 2. So that's 56 over 2, which is 28. So that's the end of that video 1.1 Introduction to Graph Theory. The next video will be 1.2 Modelling with Graphs and Networks.